The purpose of a proof by induction is to prove a statement is true for all natural numbers n. So this is to prove statements for all natural numbers n. So, or very occasionally natural numbers after a certain point. So the way it works is the steps are firstly what's called the base case. So we first prove the statement for n equals 1, or sometimes a slightly different value. If it starts at, say, if the statement isn't valid until n is 4, sometimes you prove it from n equal to 4, but in that case the question will make clear. The second step is the assumption. In this step, we assume the statement is true for n equals some number k. In the third step, which is called the induction step, we show that our assumption implies the statement is true for n equals k plus 1. And then the fourth step is to conclude. So what have we done then? We proved it's true for n equals 1. We assumed, without proving anything, that it's true for n equals k. We showed if it's true for n equals k, it must be true for n equals k plus 1. That's what step 3 shows. But because it was true for n equals 1, this induction step implies it's true for n equals 2, and that implies it's true for n equals 3, and that implies it's true for n equals 4, and so on. So what you have to write in the conclusion is pretty much always something along the lines of, since it is true for n equals k, I'll just reword that. If it is true for n equals k, it is true for n equals k plus 1, and we know it is true for n equals 1, so it must be true for all natural numbers n. So this is the kind of conclusion you'll write down pretty much every time. So all of these steps are necessary in your answer, and induction questions, it's quite important that your answer has all of these things, otherwise you won't get all the marks. So we said it's for proving statements involving natural numbers or positive integers. So just another piece of notation we might need is that z plus, this is the set of positive integers. So for many people, this is the same as the natural numbers n, but some people take the natural numbers n to include 0, whereas positive integers does not include 0. So sometimes you'll see n belongs to z plus. Okay, let's see some examples then. So what kind of things can we use this to prove? Well, one thing we can use it to prove is many of the summation formulas. So we saw other ways of proving them, but the most standard way of proving results like this equals a half n plus 1 is by induction on n. And same for the others. So we'll just do one of them. We'll do the one with cubes. So question, prove sum r equals 1 to n, r cubed equals n squared over 4, n plus 1 squared. So we'll do it by induction. So what was the first step, the base case? Well, is it true for n equals 1? So if n equals 1, we have the sum r equals 1 to 1 r cubed, which is just 1 cubed. And then if n is 1 on the other side, we've got 1 squared over 4, 1 plus 1 squared, which is also 1. So we can say true for n equals 1. Not much to do there. Second step, assumption. Assume the statement is true for n equals k. And not only am I going to write that down, so it is important to write this down, I'm also going to say exactly what that means. That means that the sum from r equals 1 to k of r cubed, we're assuming to be equal to k squared over 4k plus 1 squared. Okay, third step, induction step. So I've made this assumption, and then I'm going to look at the sum from r equals 1 to k plus 1 of r cubed, which I can split up. I can split it up as the sum from r equals 1 to k, and then I can add the last term, k plus 1 cubed. And then I can use my assumption to replace this thing with my assumption here. So this is k squared over 4k plus 1 squared. And then I've still got this term on the end, this k plus 1 cubed. And then I somehow have to do something with this, because I want to show, what I'm aiming for is to show the statement is true for k plus 1. So what I want to do is I want to get that this thing is equal to k plus 1 squared over 4k plus 2 squared. That's what I'm trying to get in these next few steps. So notice k plus 1 squared is a factor. Well, k plus 1 squared over 4 is a factor. And then inside we've got k squared plus 4 lots of k plus 1. And then we're nearly there now, because this is k squared plus 4k plus 4, which is also k plus 2 squared. So that's very good. That's what I wanted. And sometimes, to make it even clearer that I've now shown it's true for k plus 1, some people would write this as this. Just to make completely clear, I've shown the statement is, and you can write a bar over k plus 1 like this if you want. Some people do that. Just to make crystal clear that I've shown that in the place of n, I've got k plus 1. So we've shown, now we can do our conclusion. If the statement is true, therefore if the statement is true for n equals k, it is true for n equals k plus 1, and we have shown it is true for n equals 1, so it is true for all n in Z plus by induction. And that's the end of the proof. And we'll just see one more example. So we could do another summation formula, but let's do something, we'll do one more summation formula. So prove for all n in Z plus that the sum r equals 1 to n of r2 to the r is 2 lots of 1 plus n minus 1 times 2 to the n. Okay, so proof. First part is the base case. So if n is 1, the left-hand side is the sum r equals 1 to 1 of r2 to the r, which is just 1 times 2 to the 1, which is 2. And the right-hand side is 2 times 1 plus 1 minus 1, 2 to the 1, which is 2. So the left-hand side and right-hand side are equal, therefore it's true for n equals 1. And then we'll assume the statement is true for n equals k, and we'll explicitly say what that means. That means we're assuming the sum from r equals 1 to k of r2 to the r is 2 lots of 1 plus n minus 1, 2 to the k. And then we'll do the induction step. So then we'll look at the sum up to k plus 1, and we're going to use our assumption to split it up as the sum from r equals 1 to k, which we'll rewrite using the induction step plus the last term, k plus 1, 2 to the k plus 1. And then we've got this expression here. And then now it's usually a good idea to think about what we're aiming for. We're aiming to get something like this, but with, oh sorry, there's a mistake in that, isn't there? It should be a k there, not an n. And same thing here. Yeah, so what are we aiming for? We're aiming for the same thing, but with k plus 1 in place of k. So let's just expand, well, let's leave 2 outside the brackets and then write everything else inside. So what goes here then? Well, we've taken a 2 out of the 2 to the k plus 1, so all we've got left is k plus 1 lots of 2 to the k. And then 2 to the k is a common factor of the last 2 terms, so we've got k minus 1 plus k plus 1 lots of 2 to the k. And then this is 2k lots of 2 to the k. And we know 2k times 2 to the k is k times 2 to the k plus 1. And this is exactly what we wanted, because it's k plus 1 minus 1 lots of 2 to the k plus 1. So it's exactly the right statement with k plus 1 in place of n. So now we can make our conclusion. Therefore, if the statement is true for n equals k, it is true for n equals k plus 1, and it is true for n equals 1, so it must be true for all positive integers n by induction. End of proof. And we'll just do one last one. Let's let n be a positive integer again. Let's let x be not equal to 1. And the question is prove 1 plus x times 1 plus x squared times 1 plus x to the 4 all the way up to 1 plus x to the power 2 to the power n equals 1 minus x to the 2 to the n plus 1 over 1 minus x. Okay, so again we'll do it by induction. So the base case, if so x here is a variable, we're not interested in x, we're interested in proving it for n. So if n is 1, the left-hand side is 1 plus x times 1 plus x squared, and the right-hand side is 1 minus x to the power 4 over 1 minus x. And okay, so this is slightly harder, but 1 minus x to the 4 is the difference of 2 squares, and then that factorizes even further, and then we can see we're going to get there the same because the 1 minus x's cancel, because x is not 1. So this gives us the left-hand side. So therefore it's true for n equals 1. Then we're going to assume it's true for n equals k. So that means that we're assuming 1 plus x, 1 plus x squared, all the way up to, so these are all being multiplied, 1 plus x to the 2 to the k. We're assuming that's equal to 1 minus x to the 2 to the k plus 1 over 1 minus x. And then we're going to look at the same thing, but with one extra term. So we'll look at the same product, and then we'll multiply by 1 plus x to the 2 to the k plus 1. And then we'll get the other side multiplied by 1 plus x to the 2 to the k plus 1. And then let's look at these terms on the top, and let's just expand the brackets. We're going to get 1 minus x to the 2 lots of 2 to the k plus 1 over 1 minus x, which is exactly the same as 1 minus x to the 2 to the k plus 1 over 1 minus x. And this is exactly what we wanted. So now we can say we're done. Conclusion. Therefore, if true for n equals k, the statement is true for n equals k plus 1, and it is true for n equals 1, so is true for all n in Z plus by induction. End of proof. And we're done. So that last example is a slightly different, more algebraic example, and just something to think about, which is not about induction, is if the modulus of x is less than 1, my question is, what is the limit? What is the infinite product? 1 plus x squared, 1 plus x to the 4, 1 plus x to the 8, and so on, if you keep going forever. So this is really the limit, isn't it, of this thing we've just been looking at. So I won't tell you the answer, that's something for you to think about, but hopefully it isn't too hard using the example we've just done. And we'll stop there.